You know that feeling when you're just staring at this mountain of information trying to get up to speed on something really complex,
Yeah, it can be overwhelming.
and you just wish someone could cut through all the noise, maybe distill the essence,
Get right to the point.
just hand you those absolute, like, game-changing insights,
Yeah.
that aha moment, simplify,
So you actually understand it.
so you can walk away feeling genuinely enlightened,
Yeah.
ready to apply what you've learned.
Makes sense.
Well, if that sounds familiar, you've definitely come to the right place.
Mm-hmm.
Today, we are taking a deep dive into two incredibly transformative forces in the world of artificial intelligence.
Really important ones.
We're talking agentic AI and the powerful orchestration framework that, well, makes it all possible, LangGraph.
That's right. And for this deep dive, we've really dug in. We've gone through a huge collection of expert video lectures, 20 of them, actually.
20? Wow.
Yeah, extracting every single detail, every explanation, trying to cover the full breadth of knowledge on this.
So really comprehensive.
Our goal is to bring you a truly in-depth, like production-grade understanding. What does it really mean for AI to be genuinely agentic?
Right, beyond the hype.
Exactly. Why it isn't just another buzzword, but actually a foundational shift for building these incredibly sophisticated, robust AI systems.
And how LangGraph fits in.
And precisely how LangGraph serves as the indispensable, the blueprint and the conductor for these cutting-edge applications.
Okay. So our mission here is clear. Provide you, the listener, with a crystal clear understanding from the basic definitions all the way through to the nitty-gritty details.
So practical implementation, how do you actually build this stuff?
Exactly. In a real-world enterprise context, you'll walk away not just informed, but genuinely enlightened about the true potential and, importantly, the practicalities of AI agents.
Let's do it.
Okay, let's unpack this. And trust me, this is where it gets really interesting.
So to really get why agentic AI is such a big deal, we first need to draw a clear line, distinguish it from what most people think of as AI today.
You mean like the chatbots we use every day, generative AI?
Exactly. Your typical chatbot, whether it's for, say, customer service or just answering quick questions, it's fundamentally reactive.
Reactive, meaning?
Meaning you ask a specific question, it gives you a direct answer. That's it. It waits for you.
Right. It feels like you're leading it by the hand, step by step. Each interaction is just one question, one response.
Precisely. Let's make that concrete. Imagine you're planning a trip, maybe to Goa.
Okay.
With the standard generative AI, you'd start by asking, what are the best dates to visit Goa? It gives you some info.
Then I'd ask, okay, what's the best way to get there from my city?
Right. You're responsible for every single query, every step. You guide the AI. It just reacts to your specific commands. It doesn't initiate anything on its own.
Okay, I get that.
Yeah.
So how is agentic AI different then?
Agentic AI, that's a whole different ballgame. It's designed to be proactive and autonomous.
Proactive and autonomous, so it takes the lead.
In a way, yes. Instead of you leading every single step, you give it a high-level goal, a general objective, like plan my trip to Goa, and then it takes the initiative, it figures out all the necessary steps, executes them on its own, and adapts if things change.
So no hand-holding. It just goes.
Pretty much.
Yeah.
It operates with a remarkable degree of independence.
Okay, let's use that Goa trip example again. How would that work with an agentic AI?
Right. So with an agentic AI, you just state your high-level goal, something like, I want to go to Goa from October 15th to October 22nd. Budget is around $1,500 for flights and hotel. Then the agent just springs into action. It proactively researches the best flight deals for those dates. It explores suitable hotels within your budget.
Wow.
It might even plan potential itineraries, check local events, maybe look at the weather forecast.
So it does all the legwork.
Exactly. And then crucially, it comes back to you with a comprehensive proposal, a well-thought-out plan. It took the full initiative to achieve the goal you set. It acts like a true planning partner.
That's a huge difference. Okay, let's take this out of vacation planning. To make it more tangible, maybe show its applicability in a production environment.
Good idea. Let's walk through a more complex real-world scenario, an automated hiring application. This really shows off the multi-stage workflow capabilities.
Okay, hiring. That's definitely complex.
Well, imagine an HR recruiter at a big tech company. Their goal, hire a back-end engineer. Needs to be remote, have 2 4 years of experience, Python, and cloud skills.
Standard tech role. How does the agent handle this?
With an agentic AI system, this whole pipeline transforms. It goes from a series of manual reactive
Like
tasks
posting ads, sifting resumes.
into a largely autonomous process. The agent's very first step is to intelligently understand that high-level goal, hire this specific engineer.
It doesn't wait for step one instructions.
Nope. It immediately starts to develop a comprehensive plan. Its brain thinks, okay, hiring involves drafting a job description, posting it, monitoring applicants, screening them, scheduling interviews, sending offers, triggering onboarding.
So it maps out the whole process itself.
Yes, and it's not just a dumb checklist. It's an intelligent, adaptive, strategic plan.
And then the execution.
Then the autonomous execution really begins. The agent itself drafts the job description.
Does it just guess?
No, it's smarter than that. It intelligently accesses internal company resources, HR policies, tech stack docs, salary bands, department responsibilities.
So it uses existing knowledge.
Exactly, to make sure the JD is accurate, appealing, compliant. Then, once it has a draft, it seeks human approval.
Okay, a human checkpoint. That's important.
Critical. And if it's not approved, or if there's feedback, the agent knows how to intelligently redraft based on that input.
It iterates.
Until it's right, until it meets the standards. And once that JD gets the green light,
It posts it everywhere.
it posts it on relevant platforms, LinkedIn, Indeed, maybe some niche tech boards. But it doesn't stop there. It constantly monitors the application flow.
What if not enough people apply?
That's where the adaptability comes in. If the volume of qualified candidates is low after, say, 72 hours, the agent proactively adapts.
Oh.
It might suggest modifying the posting, broadening requirements slightly, changing keywords, or it might explore posting on different platforms. It doesn't just sit and wait. It adapts.
That's impressive. Okay, so applications come in.
Then it autonomously screens the resumes. And this isn't just basic keyword matching. It's intelligently evaluating candidates against the JD criteria.
So it can shortlist candidates on its own.
Yes, shortlisting those who really fit, maybe flagging some stretch candidates, all without needing a human to look at every single resume initially.
That saves a ton of time.
Huge time saver. Then for the shortlisted ones, it schedules interviews, sends calendar invites to candidates and interviewers. It can even provide pre-prepared question banks for consistency.
Manages the whole scheduling mess.
Exactly. And once a candidate successfully gets through the interviews,
Offer time.
the agent drafts the official offer letter, accesses comp data, benefits info, legal templates to make it precise and compliant, sends it out.
And if they accept?
Upon acceptance, it triggers the entire onboarding process. Welcome emails, IT access requests, laptop provisioning, scheduling, intro meetings.
Wow. So the human involvement is minimal.
Really minimal. It mostly revolves around granting permission at critical points, like approving the final offer, or intervening only if something goes seriously wrong, the very bad situations our sources mention.
Which frees up the HR team for more strategic stuff.
Absolutely. More human-centric tasks. This hiring example really shows this isn't just about simple chatbots. It's about building sophisticated, resilient systems.
Okay, so that example makes it clear. Let's break down the core characteristics that really define these agentic AI systems.
Right. First and foremost is autonomy.
We've used that word a lot. What does it really mean here?
It's not just executing tasks. It goes deeper. It's about independent decision-making.
Like deciding who to shortlist.
Exactly. Or intelligently deciding when to use a specific tool. Like knowing it needs the email API to send that follow-up. It's the AI exercising judgment within its boundaries.
But that sounds potentially risky. How do you control that autonomy, especially in like a big company FANG level production environment?
Excellent question. Controlling autonomy is absolutely paramount. Reliability, safety, they're non-negotiable. One key way is defining scope.
Limiting what it can do.
Precisely. You clearly limit which tools, actions, or decisions the agent can make on its own. You might say, screen resumes, reject obvious non-fits, but ask me before rejecting anyone post-second interview. Setting clear boundaries.
Makes sense. What else?
The human in the loop. This is crucial, and it's more than just asking for input. It means inserting explicit, mandatory checkpoints.
Like the JD approval we talked about.
Exactly. The agent drafts the JD, but must get human permission before posting it publicly. It's a safeguard. And importantly, these pauses can be indefinite. The system waits for the human, even if it takes days.
Unlike systems that might time out.
Right. That indefinite pause is key. We also need robust override controls.
Like a big red stop button.
Sort of. Mechanisms allowing a user to stop, pause, or even change the agent's behavior midstream. A pause hiring command. Or maybe reprioritize this task.
Giving humans ultimate control.
Always. And finally, guardrails and policies. These are hard-coded rules. Ethical boundaries. Things the agent must follow, no exception.
Examples.
Never schedule interviews on weekends. Do not use informal language in official comms. Or maybe ensure diversity metrics are tracked at each stage. Non-negotiable operational parameter.
Got it. Autonomy, but carefully controlled. What's next?
Next is being goal-oriented. The agent stays focused on its high-level objective, even if things change.
So it doesn't get easily sidetracked.
Right. If the goal was hiring 5 full-timers, but the budget changes midway to needing 3 freelancers instead.
The agent adapts.
It adapts its entire plan and execution to meet the new objective. It stays focused on the ultimate goal.
And that adaptability leads us to the next characteristic, right? Planning.
Exactly. Planning is core. It's the agent's ability to break down that high-level, maybe fuzzy goal into a structured sequence of concrete actions or sub-goals. It's internal roadmap.
But you mentioned it's not just a one-time plan.
Correct. Planning is iterative. It's a cycle. Plan, execute. Oh, that step failed or is impossible.
Right.
Replan based on the new info. Re-execute.
It keeps trying and adjusting until the goal is met.
Precisely. This iterative refinement is key for handling real-world messiness.
And how does it actually create these plans?
Typically involves 3 steps. First, generate multiple plans.
Brainstorming options.
Yes. For hiring, it might consider focus on internal referrals first, go straight to external portals, engage agencies. It explores different strategies.
Man.
Second, evaluate those plans. Assess each strategy based on criteria like efficiency, cost, risk, tool availability, alignment with constraints.
Weighing the pros and cons.
Exactly. And third, select the best plan. Based on the evaluation, it chooses the optimal path. This could be autonomous, human-guided, or based on a preset policy like always pick the lowest risk option.
Okay, so planning is sophisticated. What underpins all this? What allows it to plan and execute intelligently?
That brings us to reasoning. This is the crucial capability, the intellectual engine.
How does reasoning apply in planning?
In planning, reasoning helps interpret the goal, break it down, identify necessary tools like realizing it needs an email API for offer letters and estimate resources and risks for each step.
And during execution?
During execution, reasoning is vital for real-time decisions. Should I interview 2 candidates or 3 based on quality so far? Or is this salary negotiation within my limits, or do I need a human?
Knowing when to ask for help.
Critical. And also for error handling.
Yeah.
LinkedIn API is down. Should I retry? Notify human? Try Glassdoor instead. Reasoning drives these essential on-the-fly choices for production success.
Makes sense. And you mentioned adaptability earlier, too.
Yes, adaptability. The agent's capacity to adjust its plan or behavior based on new info, changes, or failures.
Like the low application volume example.
Exactly. If applications are too low, it doesn't just fail, it adapts. Broadens the posting, adjusts the JD, seeks candidates differently. It learns and course corrects dynamically.
Okay. And the last characteristic.
Context awareness, which is essentially the agent's memory. To operate consistently and learn, agents need memory.
Like remember things.
Right. Both short-term and long-term. Short-term memory is for the current session, like a sticky note. Candidate B has 3 years experience, info from the last step. It's temporary but needed for flow.
Then long term.
Long-term memory stores persistent knowledge, rules, past experiences. Like that guardrail, never send an offer without human approval. Or maybe performance data from past hiring cycles to improve future strategy. Ensures consistency and learning over time.
Okay, those characteristics paint a clear picture. Now, what about the high-level architecture? What are the main components inside an agentic AI system?
Good question. Generally, you'll find 5 core high-level components working together.
Component 1.
The brain. This is usually the LLM itself, the core intelligence. Handles goal interpretation, planning, reasoning, tool selection, natural language communication. It does the heavy thinking.
Okay, the brain. What's next?
The orchestrator. This is super important. It takes the plan from the brain and actually executes it step by step. Manages the control flow, transitions between tasks, ensures the plan is followed or adapted.
And you mentioned LangGraph fits here.
This is exactly where LangGraph shines. It is the orchestrator.
Got it. Component 3.
Tools. These are the external services or APIs the agent uses to act in the world. Email API, calendar API, HR system API, web search, the agent's hands and feet.
Makes sense. Allows it to do things. 4th.
Memory. As we discussed, this component manages both short-term context and long-term knowledge. Crucial for consistent, informed behavior.
And the 5th component.
The supervisor. That's the human element. Absolutely essential in production. Provides oversight, approvals, override control. Ensures accountability, safety, and alignment with human intent.
All right, that's a really solid foundation on agentic AI. Now let's pivot to the frameworks. How do we actually build these things? Many listeners probably know LangChain.
Yes, LangChain has been foundational, really pioneering in the space of building LLM applications. It gives you excellent building blocks.
Like what?
Well, a unified interface for different LLMs, OpenAI, Anthropic, Hugging Face, makes swapping easy, great tools for prompt engineering, and retrievers, crucial for RAG for pulling in data from vector stores or knowledge bases.
And the core idea is chains, right? Linking components together.
Exactly. Chains are the main abstraction. You link things sequentially. Prompt LLM output parser. Output of one step feeds directly into the next. Very neat for linear processes.
So LangChain is good for what kind of tasks?
It's ideal for simple linear workflows. Basic chatbots, text summarizers, multi-step things that are mostly sequential, like generate a report, then summarize that report. Basic RAG applications, too, where the flow is straightforward.
Okay. Now you said earlier, here's where it gets really interesting. This implies LangChain has limits, especially for the agentic stuff we just discussed.
Precisely. While LangChain is great for linear chains, real-world agentic apps are rarely linear. They need dynamic, non-sequential flows. And that's where LangChain, by its design, starts to struggle. This struggle basically forced the need for something new, like LangGraph.
Okay, challenge number one.
Control flow complexity. LangChain's linear structure just doesn't have built-in ways to handle essential nonlinear logic. Think basic programming stuff, conditional branching, ifelse, loops, repeat until done, or jumping to different steps dynamically.
How did people handle that in LangChain then?
They had to write a lot of custom Python code outside of LangChain's nice abstractions, we call it glue code, essentially forcing a linear framework to behave non-linearly through manual scripting.
And the downside of that?
As projects get complex, all that glue code makes them incredibly hard to maintain, debug, and collaborate on. Especially in a team or enterprise setting, it becomes a tangled mess.
Okay, control flow is tough. What's challenge number two?
This one's maybe even more fundamental. State handling. Managing the evolving workflow state over time.
You mean like tracking the JD status, number of applicants, etc.?
Exactly. Complex workflows need a central state, a blackboard holding all current data. LangChain's built-in memory is mostly for chat history, not this kind of evolving, persistent workflow state.
So how did LangChain users manage state?
Manually, passing around a Python dictionary, updating it explicitly at every single step of a potentially long chain.
That sounds messy.
It's incredibly hectic, very error-prone, adds huge overhead. Imagine managing a project by shouting out the complete status after every tiny update. LangChain workflows are basically stateless in this architectural sense, forcing developers to manage state manually, externally.
Yikes. Okay, third challenge.
Event-driven execution. Real-world workflows often need to pause and wait. Wait 7 days for applications. Wait for an API callback. Wait for human input.
Then LangChain chains run
How?
synchronously. They run straight through without stopping. They aren't designed for these long, arbitrary pauses.
What were the workarounds?
Things like Python's time.sleep for short waits, or complex external monitoring. Both are inefficient, waste compute resources during the wait, and are fragile, prone to crashes during long pauses with no easy recovery. Not suitable for production systems needing long waits.
Right. Reliability is key. Which brings us to challenge 4.
Fault tolerance. Production systems will fail sometimes. Server crashes, network glitches, LLM errors. You need built-in ways to retry failed steps and, crucially, recover resume from where it left off.
Does LangChain offer that?
No intrinsic retry or recovery logic out of the box. Again, it requires extensive custom glue code to build that resilience.
Yeah.
Makes the system less robust.
Okay. Challenge 5 must be the human element again. You guessed it. Human in the loop. We know human approval is often critical. JD approval off review. LangChain chains, being synchronous, struggle with long human delays.
How so?
If a manager needs 24 hours to review a JD, you'd have to break the LangChain flow into 2 separate chains, manually save the state from chain 1, wait, then manually load it into chain 2 after approval.
More complex, brittle glue code.
Exactly. It can't just pause indefinitely and resume gracefully without a lot of manual, fragile scripting.
Number 6.
Nested workflows. The ability to treat a complex sub-process like conduct interview, which has its own steps, as a single node within a larger workflow. Think subgraphs. Essential for modularity, reuse, and building multi-agent systems.
And LangChain do that? Nest workflows.
Fundamentally, no. That capability isn't supported in its core design. This severely limits building large-scale, modular, enterprise-grade agents.
Okay, final challenge. Number 7.
Observability. Monitoring, debugging, auditing in production. You need to see why an agent did something, track LLM calls, see state changes. LangChain integrates with LangSmith for this, which is good, but
There's a catch.
yes, LangSmith tracks LangChain's own components well. But it cannot see inside all that custom Python glue code you wrote for control flow and state management.
Ah, so you only get partial visibility.
Exactly. Partial observability makes deep debugging and auditing incredibly difficult, sometimes impossible, in a production system where you need full visibility.
Okay, so those are some pretty significant challenges for LangChain when building complex agents, which leads us perfectly to LangGraph. What is it, and how does it solve these issues?
Right. LangGraph is an orchestration framework specifically engineered from the ground up to build stateful, multi-step, and event-driven workflows using LLMs.
Purpose-built for this stuff.
Exactly. It's ideal for designing both complex single-agent apps and intricate multi-agent systems needing that autonomous, proactive behavior.
You called it a flowchart engine for LLMs earlier.
That's a great analogy. Instead of just linear chains, you define individual steps as nodes, you define connections between them with edges, and you specify the logic governing those transitions, creating dynamic paths.
And it uses graphs.
Its core abstraction is the workflow as a graph. Graphs are inherently nonlinear, so LangGraph can naturally model, visualize, and execute the most complex, branching, looping, adaptive workflows.
And no glue code.
It eliminates the need for that messy, brittle, custom glue code. The logic lives in the graph definition.
Okay, let's revisit those 7 LangChain challenges. How does LangGraph tackle control flow complexity?
It provides built-in first-class constructs, conditional branching, loops, jumps, all defined declaratively within the graph. No external Python glue code needed for flow control.
What about state handling? That seemed like a big one.
State is a first-class citizen in LangGraph. You define a central state object, often a Python typedict, or a pydantic base model for structure and type safety.
Like a well-defined project binder.
Exactly. This single state object is accessible and mutable by every node. The entire execution is inherently stateful. The state evolves cleanly as the workflow progresses.
And the pausing issues. Event-driven execution, fault tolerance, human in a loop.
LangGraph nails these with the core feature, checkpointers. It can save the exact state of your workflow at any point in memory or persistently to a database.
What does that enable?
Indefinite pauses, wait days for human input, resume seamlessly, and trivial recovery from failures, server crashes. Just restart, LangGraph picks up exactly where it left off using the last checkpoint. Maximum resilience.
Nice. Nested workflows, subgraphs.
Fundamental concept in LangGraph. Any node can be an entire separate LangGraph. This gives you amazing modularity, reusability, and it's essential for building multi-agent systems where agents delegate tasks.
And finally, observability. Does it fix the partial visibility problem?
Yes. Because there's no hidden glue code outside of the graph, LangGraph's integration with LangSmith provides complete end-to-end observability. Track every decision, every LLM call, every state change, the exact path taken. Debugging and auditing become far easier.
Okay, LangGraph sounds powerful. What are the actual pieces you use to build with it? The building blocks.
3 main things. First, the state. That central data store we discussed, defined with typedict or pydantic, mutable, passed around everywhere.
Second.
Nodes. These are your workhorses. Simple Python functions that do specific tasks. Each node gets the current state, does its work, and returns a dictionary of updates to the state.
And third.
Edges. They define the flow between nodes. You use add edge for simple A to B sequential steps.
And for the clever branching.
You use add conditional. Here, you give it a function that looks at the current state and returns the name of the next node to go to. That's how you implement if-else logic dynamically.
Nodes, edges, state. Then what?
Then graph compilation. You take your defined nodes and edges, and LangGraph compiles them into an executable workflow engine ready to run.
Okay, let's see some examples. Start simple, maybe sequential workflows, just step-by-step tasks.
Sure. A non-LLM example, a BMI calculator. State holds weight, height, BI category. 2 nodes. Calculate TBMI, takes weight height from state, calculates BMI, updates state, and label BMI. Takes BMI from state, categorizes, updates state.
Flow is just start, calculate, label, end.
Simple, sequential, but shows the state flowing through.
Okay, now an LLM-based sequential example.
Let's do prompt chaining to generate a blog post. State holds title, outline, content.
No.
First node, create outline. Takes title from state, calls an LLM, generate outline for title, updates outline in state, second node, dot create blog. Takes title and the new outline from state, calls another LLM, write blog post using this title and outline, updates content in state.
Flow is start, create outline, create blog, end, still sequential.
Yes, but notice the key insight. State carries info forward effortlessly. Create blog easily accesses the outline from the previous node. No complex manual passing needed like in simpler frameworks. LangGraph handles state propagation inherently.
Got it. Now, what about doing things at the same time? Parallel workflows.
Yes, very powerful. Run multiple independent tasks concurrently, then merge results.
Non-LLM example first.
Okay, batsman stats calculator. Goal. Simultaneously calculate strike rate, boundary percentage, balls per boundary from input runs, balls, fours, sixes.
State holds inputs and outputs.
Oh, right. State has runs, balls, fours, sixes, plus the calculated strike rate, balls per boundary, boundary percent, summary, flow. Start, run, calculate strike rate, calculate boundary percent, and parallel. Merge results in summary node end.
What's the key learning for parallel updates?
Crucial point. Nodes in parallel branches should return only the specific parts of the state they updated, partial updates. Avoids conflicts. If each returned the whole state, LangGraph wouldn't know which version to keep when merging.
Like collaborating on a shared doc, only save your paragraph, not the whole thing.
Exactly. Okay, now an advanced LLM parallel example. Essay evaluation.
Evaluating based on different criteria simultaneously.
Right. Evaluate clarity, analysis, language quality, all in parallel using separate LLM calls. Then generate summary feedback and an average score.
State would need fields for the essay. Each feedback type scores.
Yep. Essay text, clarity feedback, analysis feedback, language feedback, individual scores, a list, overall feedback, average score, flow, start flet, run evaluate language, evaluate analysis, evaluate thought in parallel, converge at final evaluation node to merge results, end.
This sounds complex. What advanced concepts does it show?
Two key things. First, structured output, absolutely vital for reliability. Each evaluation node uses a pydantic schema, say evaluation schema feedback.string score.in010. You use model with structured output to force the LLM to return JSON matching that schema.
No messy, free-form text-breaking things.
Precisely. Guarantees machine-readable output, essential for production. Second, reducer functions.
Yeah, they do.
They intelligently merge outputs from parallel branches. For individual scores, each parallel call returns one score. A reducer like operator.add appends each score to the list in the state. It doesn't overwrite, it accumulates. Safely combines parallel results.
Okay, parallel is powerful. Now, the really dynamic stuff, conditional workflows, the branching logic.
Yes, the if-else of workflows, where the path changes based on data, essential for adaptable agentic behavior.
How does LangGraph do this?
Using add conditional works. Instead of a fixed next step, you provide a function. This function checks the current state and returns the name of the next node to execute based on conditions.
Can you give a simple non-LLM example?
Conceptually, a quadratic equation solver. It calculates the discriminant. If positive, go to 2 real roots node. If 0, go to 1 real root node. If negative, go to complex roots node. The state, discriminant value, determines the branch.
Makes sense. Now, a practical LLM example.
A sophisticated customer support workflow. Goal.
Yeah.
Give tailored replies to reviews based on sentiment.
How does it start?
Starts with the customer review text. First node, LLM extracts sentiment, positive or negative, using structured output. Then, a conditional edge based on that sentiment.
If positive.
Simple path. Branches to a frame positive response node. Crafts a nice thank you message.
If negative.
Then it gets more complex. Branches to a diagnose a negative review node. This LLM does deeper analysis, extracting issue type, UI, performance, etc. Tone, frustration, anger, urgency, again using structured output, adds this diagnosis to the state.
So it understands the negative review better.
Exactly. Then, using all that diagnostic info, it goes to a frame negative response node. This node crafts a highly tailored, empathetic reply considering the specific issue, tone, and urgency.
Not just a generic, sorry for the trouble.
Definitely not. This shows how conditional logic lets agents handle diverse situations with dynamic, intelligent, tailored responses far beyond simple scripts.
Okay, this deep dive makes LangGraph sound incredibly powerful. So the big question, when do you use LangChain and when do you absolutely need LangGraph? Let's clarify that.
Good question. LangChain remains ideal for simple linear workflows. Basic prompt chains, text summarizers, straightforward RAG where the flow is predictable and sequential. It's great for getting started and for less complex tasks.
And LangGraph is for.
It's your go-to for complex, nonlinear workflows. Anytime you need conditional branching, loops, human-in-the-loop steps, multi-agent coordination, asynchronous event-driven execution, or robust fault tolerance and recovery. If your workflow looks like a flowchart with decision points, you need LangGraph for a production-ready system.
So they serve different complexity levels, but do they compete or work together?
That's a crucial point, often misunderstood. LangGraph is built on LangChain. They work hand in hand. LangGraph is not a replacement.
Ah, so it leverages LangChain's parts.
Exactly. It's built on top of LangChain. When you build sophisticated agents with LangGraph, you still use LangChain's core components.
Like which ones?
You'll use ChatOpenAI or ChatAnthropic from LangChain for LLM interactions. You'll use Prompt Template from LangChain for crafting prompts.
What about data handling and tools?
You'll heavily use LangChain's retrievers, document loaders, text splitters, and various tools, search, calculator, APIs, all from LangChain to let your agent interact with data and the world.
So what's the role of each then?
Think of it like this. LangChain provides the fundamental components or power tools interacting with LLMs handling data. LangGraph provides the intelligent orchestration framework to chain, branch, loop, and manage state across those components.
Making the complex, robust agents possible.
Exactly. They function hand in hand to create production-grade AI systems. LangChain gives you the instruments, LangGraph gives you the conductor and the score.
That's a great analogy. You really need both for the full orchestra.
Precisely. You'll see them combined in almost any serious, real-world agentic application aiming for robustness and scalability.
Wow. We've covered a lot. From defining agentic AI, its characteristics, the challenges with linear frameworks,
To the solutions LangGraph provides. Control flow, state management, event handling, fault tolerance, human loops, nesting, observability.
it's clear LangGraph is key for building these resilient, production-ready AI agents. Agents that can plan, reason, adapt, and handle complex scenarios.
It really enables that shift from reactive tools to more autonomous collaborators.
So, reflecting on all this, what does it mean for the future? Are we just building better tools, or is this something more fundamental? Are we engineering truly autonomous collaborators?
That's the big question, isn't it? Based on what we're seeing with frameworks like LangGraph, designed specifically for stateful, reasoning, adaptable systems, it certainly feels like we're leaning heavily towards that latter, more transformative vision, engineering collaborators that reshape how we work and interact with tech.
A profound thought. So for listeners wanting to explore this further,
The next step is probably to start experimenting. Try building a simple LangGraph agent. Maybe automate a small, tedious task you do often. The LangGraph documentation is excellent. Getting hands-on is the best way to really grasp its power.
you might just find yourself building the future of AI applications.
Couldn't have said it better myself.